All right, welcome to section 4.4 from our college algebra book, Building Quadratic Models from Verbal Descriptions and from Data. These are all applications of the parabola. We're going to start with this paragraph right here. It says build quadratic models from verbal descriptions. In economics, the revenue R in dollars is defined by the amount of money received from the sale of an item and is equal to the unit pricing P in dollars of an item times the number X of units actually sold. So it's the price times how many you sold. The law of demand states that P and X are related as one increases and the other decreases. The equation that relates P and X is called the demand equation. When the demand equation is linear, the revenue model is a quadratic function. So the demand equation has to be linear to make this happen. So here's the demand equation, and we're going to put that in together with the price, and we get this nice quadratic here. So let's write in this area right here, get the quadratic, and we graph this quadratic, and it's an upside down parabola. So basically, we've kind of seen this before in the past. If we have if we sell our calculators for not enough money, then we don't make any money, any revenue at all. If we charge too much, we don't make any revenue, but somewhere in the middle, the price is just right. Now, when you're graphing this out and figuring this out, you're going to want to, on a calculator, you definitely want to change your scale, because look, it goes clear up to 800,000. The next application is basically what we did in the last chapter. We put one equation into the other equation. So here we have 2x plus 2w is equal to 2,000, and that would be the perimeter, and it gives us area. Trying to maximize the area, so you're going to combine the perimeter equation into the area equation, and that's done right here. And it turns into a quadratic, and it's an upside down parabola quadratic situation, and you have a highest point. And you can find that by the vertex equation or graph it on the graphing calculator. And again, you have to change your scale here and think about the domain of the function. Projectile motion is quadratics. So you can see that as something is flying through the air here, it follows a quadratic type situation, and that would be all analyzed in this part right here. The next example is the Golden Gate Bridge, and they're using the picture of the Golden Gate Bridge to make a model of how the shape of the bridge is. And then there's your vertex in the center, and then you can go over, it goes like 2,100 feet and then up so much, and then 2,100 feet back this way and up so much, and there's a model of the bridge. You can also have data, so you can do put your data in the calculator. Instead of choosing linear regression, you would choose quadratic regression. So there's a positive quadratic and then a negative quadratic relationship, and exemplified in those two things. All right, and so we have age and then percent divorced. So if you're young, there's not a lot of divorced people. If you're old, then there's not a lot of divorced people, and if you're in the middle, that's where all the divorced people are. So they're relating that in an upside down parabola type situation. All right, let's go ahead and go through an example here. This would be an example of we minimize that, and it's still there. Yep, it's still there. So this would be revenue kind of situation. So we have the price P in dollars and the quantity sold X of a certain product obey the demand equation. And we know that R, there's my pen working, and I can pull up a pen here. So we know R is equal to X times P. It says find the model that expresses the revenue R as a function of X. So I'm going to take this price here, which is related to the number sold, or the number sold, and put it in for P. So R is equal to X times P, and P is -1/3 x plus 100. So I'm going to distribute that through, and you're going to see the quadratic. Negative 1/3 x squared plus 100 x. So there's my upside down quadratic. And it answered the question. It says, express the model as a function of x. So there it is. So the revenue is dependent upon x, which is the number sold, correct? Yes, the quantity sold x. Okay, the domain of the function. The domain of the function can be seen here, because if x was 0, then there'd be no revenue, and you can't have anything below that. So the lowest, so this is part A, this is part B, and I want the domain of R. Come back, pen, there we go. So 0 would be the smallest. Now, right here, this could be equal to 0. So if x was 300, this would be negative 100 plus 100 would be 0. So we'll see that when we graph it out. So 300 would be the highest. There's the domain of the function. So what's the revenue if 100 are sold? So we can just put 100 in here and get an answer. So we're looking for R of 100. So we're just going to put 100 in for x. So it'd be negative 1/3 times 100 squared, in parentheses, plus 100 times 100. That'd be a good thing to type into the calculator. The answer is 66,000. Let me count all my sixes here. No, it's $6,667.67. It's all the sixes. So 6,667.67. All right. Now we want to maximize the revenue. So we're going to maximize the revenue here. So this is an upside down parabola. We can do negative b over 2a, or we can graph it, or whatever. Let's go ahead and go to the graphing calculator so you can see the domain as well. So calculator and full screen on. Oops, lost the calculator. There we go. Clear. Y equals negative 1/3 x squared plus 100x. All right, so I need to go to my window key here, and I'm going to do 0 to 300. Scale, I'm going to do a scale of 30 because I always do about 10%. And then my revenue isn't going to go to the negative world. Okay, and I'll do a revenue of 10,000. Scale of 1,000. And again, you may have to readjust this and graph. So you can see it's perfectly, it goes up and it goes back down. And from 0 to 300, it's like exactly, and I think I even nailed it in the center. So I go to second and then calculate maximum. Over to the left a little bit. Enter. Go to the right a little bit. Enter. And there's the center. So you have to ignore that extra 0.0001. It's going to be X is 150, and then the amount of money is 7,500. So your revenue is 7,500. All right, let's go back to the problem here. So for part D, it's 150. So let me put that in here. I'll go to a different color. I don't see blue anymore. That's purple. I don't know where blue went to. Huh, that's weird. Like the color disappeared. That's black. I got like red on there twice. Weird. I don't know what happened. Anyway, I guess I'll just use this one. Okay. So from the and we could do negative b over 2a. If we did negative b over 2a, it would be at 150, wouldn't it? Because it would be negative b. So it'd be negative b, which would be negative 100, over 2a, which would be 2 times 1/3, and it's a negative 1/3. Okay, so it would be negative b over 2a, so it should be 150. 2/3, yeah, because the 2 would divide into that, making it 50, and the 3 would come up and multiply it. It'd be 150. So it's at 150. So the negative b over 2a does tell us 150 as well. So it happens at 150. And then we saw the graph, 7,500. Okay. And then what price? Well, we know the x and we know the revenue, right? Because the revenue is the function here. So if we want to know the price, we got to solve this equation right here. So the revenue is 7,500. And then x is 150. And then p is what we're looking for. So 150 times what makes this? Well, it'd be 50. So you divide that into there, it's 50 times. So the price would be $50. Because 50 times the 150 makes this. I'm going to pause this for a second and then talk about the next problem. All right, here's the next example. So enclosing a rectangular field. Beth has 3,000 feet of fencing available to enclose a rectangular field. Express the area of the rectangle as a function of x, where x is the length of the rectangle. For what value of x is the area of the largest, what's the maximum area. So this is like combining the equations together, like the helper equation, all that kind of stuff we talked about before. All right, let's go with this color. So we have a rectangle. It has 4 sides. The sides aren't wavy like I just made there, right? So this is going to be x and y and x and y. It's so sensitive. It like keeps popping up like that. Get tired of it. 2x plus 2y equals the perimeter, which is 3,000. So differently, if we divide all that by 2, x plus y is equal to 1,500. The area would be area is equal to length times width, which would be x times y. Now I can make this all be in terms of x by subtracting this x over, right? So y equals 1,500 minus x. So this here is going to get substituted in for y. The area is my governing equation here. So area is equal to x times 1500 minus x. And then I can distribute, and you can see the quadratic. Area equals 1500 x minus x squared. And you can do the negative b over 2a again and find the maximum again. So x is the largest. So it is an upside down parabola, correct? A sad parabola, because it's negative that. So negative b over 2a. So x equals negative b over 2a. That's the h coordinate of the vertex. So it's going to be negative 1500 over 2a. And a is negative 1, isn't it? So it's going to be 750. So 750. Oh, this thing's so touchy. 750 is going to be 750 feet. And it's going to be the maximum. And then it wants to know the maximum area. Okay. Well, if that's 750, then this is your helper equation right there. So if x is 750, then y has to also be 750, right? Because you got to be 1500. So y is equal to 750 feet as well. So I made a square. Okay, if you want to know the area, you would multiply the 750s together, wouldn't you? So area is 750 squared feet squared. And then 750 times 750 is a whopping 562,500. Bring the calculator up here. And, whoops. Bring the calculator up here and on. And quit. 750 squared. $56.25 double O's. So it's 56.25 double O's feet squared, comma, equals. All right. Now I'm going to pause it and bring up the next problem. All right, here's the third example. A parabolic arch has a span of 120 feet and a maximum height of 25 feet. Choose suitable rectangular coordinate axis and find the equation of the parabola. Then calculate the height of the arch at points 10 feet, 20 feet, and 40 feet from the center. So we're going to go over 10 feet, 20 feet, and 40 feet from the center. So here we go. We need to come up with some kind of a XY axis situation. There's my XY axes. Here's my parabola. Whee! So this would be 0. And it's a span of 120 feet. This would be 120 feet. And it has a height of 25 feet. And that would be in the center because it's a parabola. So this would be 60. And this would be 60, comma, 25. All right. So if we're going to write the equation of this, that would be the point 0, 0. So we have 0 is equal to a x, which would be 0, minus h, which would be 60 squared, plus k, which is 25. So I'm using the vertex form. And this would be the point 0, 0 here, right? So x and y are 0. So now 36 times 36 is not 36 times 36. 60 times 60 is 3600. That's what I was trying to say. So 0 is equal to 3600 times a plus 25. All right, now I'm going to subtract over the 25 and divide by 3600. So negative 2500 over 3600. Oops, undo. 3600 is equal to a. I need to reduce that fraction. So basically 25 goes into 25. How many times does 25 go into 3600? Well, it's late at night and my brain's tired, so here we go. On 3600 divided by 25. That's how many times it goes in there. 144. Oh, that kind of makes sense. So the answer for this would be negative 1 over 144. So we have y is equal to a, which would be negative 144, negative 1 over 144. And then it's going to be x minus h, which is 60, and then squared, plus k, which is 25. All right, now we want to know the y value, the height, 10 feet from the center. So we're 10 feet from the center, 20 feet from the center, 40 feet from the center. So what are we talking about here? Let's draw some lines in here. So I'm going to go below. So if I go 10 feet below, then this would be 50. So all you have to do is put 50 into the equation. And if I want to go 20 feet below, then I would go down here, which would be at 40, correct? If I go 40 feet below, then I'd be clear down here at 20. My scale's off a little bit, isn't it? But you get the idea. So you're going to put 50, 40, and 20 into the equation. Likewise, if you go 10 feet above, you would put in 70. And then 20 feet above, you'd put 80. And then you would go 40 feet above, you would put in 100. And then those y values would be the height of my arch here. So the fastest way to do that would be to go to the graphing calculator and go to y equals, clear. So it's negative 1 divided by 144, left parenthesis, then it's x minus 60, and then squared, and then plus 25, because that's the vertex. Enter. And now, if you go to table set, which is above the window key, so second table set, and we want to change it to ask. And now we can go to the table. Table's above graph. Now I can type in anything I want. So what were some of the numbers again? The center was 60, right? So then that's 25 feet up. Then it said to go 10 feet away. So I want to know the answer for 50. And Ooh, it doesn't come down very much, does it? I think that's why they wanted you to do the problem. And then 70. All right. And then 20 feet away would be, what did I say, 40 and 80? 40 and 80. And the whole point of this function is you could do anything. Now 40 feet away would be 20 and 100. So 20 and 100. Now it's really dropping, isn't it? And those would be the same, wouldn't they? Because it's a parabola, equally distant from the center. All right, so hopefully this has been helpful. This will help you to do the assignment in this section. Let me go down here and boom, and